This is the firmament is real, or 100% proof that the firmament is real. I actually put this proof in several of my first videos, but a lot of people didn't really catch that that was what was in there. So it was also in my Flat Earth Fully Explained video, which many times has been blocked worldwide and pulled from the internet. What this information is, first we'll start with the information about high altitude lightning and how scientists admit that it's the very top of the atmosphere and that it's created, that lightning and sprites and high altitude lightning and sprites and elves are created on the other side of the dome. And it's in a National Geographic piece. I'll link it here. Every time I've used any clips from that piece, they have heavily copyrighted it and removed it from YouTube, so I can't post using that. So you saw that these guys, the Flat Earth Bros, they saw it in my movie, I think, and then they went and made a piece about it. And then they went and made another piece about it here as well. And you can see it was originally in my Heaven and Earth, and also the Flat Earth Fully Explained video, which had the actual full National Geographic piece in it, where they discuss that it's the top of the atmosphere and that they can't get to the other side of it to confirm their findings. So it's another admission that we can't make it to space. So after that, though, there's this amazing proof, and I hate to use other people's information, but I think it's worthwhile here. This is Rob Skiba, who does amazing work. You guys know him. He's amazing. So you'll see these CIA documents that were approved for release in 2000, and you'll see that this is actually the Scientific Council of the Institute of Physics of the Earth in the USSR, and that they argued for these findings at the geophysical year. It's about light scattering in the high atmosphere, so some properties of atmospheric indicatrices of light scattering by Pyaskovskaya, Fasenkiba, the Astrophysics Institute, the Academy of Sciences in Kazakhstan, the USSR. This is done in 1957, but it shows you that even at that time the Russians knew there was a firmament. Determining the coefficient of atmospheric transparency from sky brightness. And you'll see they use several methods to actually determine differences of light in the sky to identify the firmament. So again, by the same author, USSR Geophysics, published in '62, Calculation of Light Dispersion of the Higher Orders. A proof is presented that the light dispersion of the higher orders can be computed from the data obtained in plain direct observations. The brightness of the sky considering all forms of light scattering. Various methods for determining the atmospheric transparency coefficient. And all of these documents as well reference the non-rotating flat Earth, or a flat non-rotating Earth. And I'll put links to them as well. Study of the dispersion of light in the Earth's atmosphere. Joint Council of Institute of Physics of the Earth, the Institute of Physics of the Atmosphere, and Institute of Applied Geophysics. The Academy of Sciences in the USSR. You can't get any higher up, scientifically. Investigation of light scattering in the Earth's atmosphere, 1957, from Moscow. 2,500 copies printed. Sponsored by an academy of the USSR, the Scientific Academy. The purpose. The book represents advances made in the study of light scattering in terrestrial atmosphere and is directed to the specialist in the field. This book is a theoretical study of the optics of terrestrial atmosphere and is supplemented with observations of the brightness of the daylight sky, conditioned by molecular and aerosol scattering of light. A new method is proposed for the derivation of the scattering indicatrix from the calculation of multiple light scattering in the atmosphere. And it shows all of the people involved, all the scientists, and different heights. Introduction, Chapter 1, Fundamental Concepts and Definitions. Weakening of light in the atmosphere, scattering of light in the atmosphere, the apparatus and methodology of the observations, a daylight sky photometer, an aureole photometer, determination of effective wavelengths, and accuracy of measurements. Brightness of the blue daylight sky. Formula for the brightness of the blue sky with consideration of first-order scattering and certain deductions from this formula. Observed brightness of the blue daylight sky. A formula for sky brightness with consideration of multiple light scattering and collation of the formula with observational data. Indicatrix of light scattering in the atmosphere, calculation of multiple light scattering, criterion for the stability of optical properties of the atmosphere, methods for determining the atmospheric clearness coefficient from the blue sky brightness. So they're able to determine the brightness put off by different objects in the sky. And they'll actually use the sun to measure against, and they'll use brightness of the sky to measure against. And also brightness of the reflection off of the dome itself, the firmament of the sky. Dissertations defended in the Scientific Council of the Institute of Physics of the Earth, Institute of Physics of the Atmosphere, and Institute of Applied Geophysics in the USSR during the first semester of 1957. Further, it says, in the dissertation, the design was briefly reviewed by 16 various models of oscillographs for experimental geophysical investigations which were developed by the author or under his direction. Some of these are series manufactures and apply also in other branches of science and engineering. Particular attention is devoted to the design of the individual assemblies of the oscillographs. Standard assemblies include type something galvanometers mounted into blocks with permanent magnets, galvanometer illumination, time markers, compact gearboxes with swivel-mounted sectors, spring-powered engines, speed regulators. All the oscillographs developed by the Institute of Physics of the Earth, which is pioneering in this field in the Soviet Union, can be subdivided into the following three groups. Oscillographs for recording short-duration processes with high speeds of the film, oscillographs for recording long duration of occasional processes at relatively low speeds of the film strip, universal oscillographs for recording various processes within a wide range of speeds of the film strip, oscillographs intended for recording long duration and occasional phenomena, earthquakes, and designed for recording with a speed of 0.1 to 2 centimeters per second for moving the film. Spring-operated mechanisms proved advantageous in this case, and therefore it was necessary to develop special speed regulators. The presence of spring-operated mechanisms and galvanometers grouped into a block with a common permanent magnet enabled reducing parasitic influences on the metering circuit, and also reducing to a minimum the power consumption of the oscillograph, which is particularly important in regions with difficult access. Universal portable oscillographs represent the widest group amongst oscillographs produced in the Institute. They are small and light and therefore convenient for expeditions. They are suitable not only for recording geophysical but any other phenomena which can be transformed into an electric current or voltage. The oscillographs are among the best produced in the Soviet Union, as well as in other countries. The developed fundamental, typical assemblies and unification of the main circuits enabled, rationalizing the design of the oscillographs and also simplifying and covering the cost of the development and manufacture of new models adapted for given conditions. First, the author considers the method of calculation of the basic elements of the oscillographs which he has developed. All the calculations were tested by practical experience and are affected by formulae which are convenient for practical use. For simplifying the calculations, nomograms, data tables, and examples are included. A fundamentally new metering system was created. A high-frequency frame galvanometer with a continuous extension pull and a method of calculation is presented for the type of galvanometer, giving results of experimental investigations which indicate the possibility of achieving a sensitivity exceeding that of loops. The conditions of optimum electromagnetic and liquid damping of frame galvanometers were investigated. The calculation is presented of the kinematics of oscillographs and of film adapters, and the phenomenon of shock was considered when switching on film adapters designed for high speeds. Formulae are derived which permit calculation of the impact force and of the time necessary for reaching a given speed. A new type of simple, compact, and reliable gearbox was developed, and the method of its calculation evolved. Other mechanisms were also considered, intended for stepped and stepless speed changes and used for oscillographs. A method of calculation is proposed of spring-operated mechanisms for oscillographs aiming at achieving maximum useful work from the energy stored in the springs. The problem is considered of ensuring uniform movement of the film strip, and various designs were developed of speed regulators with low rated RPM which are capable of taking up a considerable excess moment generated by the springs. A method of calculation is presented of a radial action centrifugal regulator. All the described oscillographs were used in geophysical investigations, i.e. in studying the physics of earthquakes by systematic recording of weak local tremors, development of a new method of deep seismic sounding of the Earth's crust, study of the vibrations of soils and of buildings caused by explosions and earthquakes, development of new progressive methods of seismic and electromagnetic prospecting of minerals, study of atmospheric phenomena, etc. The oscillographs developed by the author are widely used, not only for geophysical investigations, but also in scientific establishments and undertakings of various ministries, and the manufacture of these instruments does not satisfy requirements. And we'll get to it here. So page 19 of 100 on this document, and we read, Doctoral Dissertation. Opponents: Doctor of Physico-Mathematical Sciences Kuznetsov, Doctor of Physico-Mathematical Sciences Polotskov, Doctor of Physico-Mathematical Sciences Rosenberg, Doctor of Physico-Mathematical Sciences Shklovsky. The dissertation represents the result of many years of study of the clear daytime sky. The observations were carried out in 12 locations at various altitudes above the sea, various climatic, meteorological, and synoptic conditions. The observations were carried out mainly during high transparency of the atmosphere and the visual range of the spectrum in the absence of a snow cover. In the investigations, 2 instruments designed by V.G. Vasenkov were used. One of these was a visual photometer of the daytime sky, intended for measuring the brightness of the firmament. The other was a photoelectric halo photometer for determining the brightness from near-sun halo and also from the sun on a surface perpendicular to these rays. The dissertation contains a certain formula of the brightness of the sky, taking into consideration only the brightness of the first order, and derived on the assumption of a flat Earth, and giving some conclusions derived on the basis of this formula. For a certain coefficient of transparency of the atmosphere, the brightness of the sky at any point is represented by derivation of 2 functions, of which one is the function of the diffusion of light, and the other is a function of the zenith distances of the sun, and of the observed point of the sky. On changing of the zenith distances of the sun, z, from 90 to 0 degrees, the brightness of the sky on the almucanter of the sun increases first, reaching a maximum for a certain value of z, and then decreases. A method is also proposed of determining the brightness of the clear daylight sky at any point, based on measuring the brightness along the almucanter of the sun, and of 5 or 6 points of the firmament located at various zenith distances. This method permits determination of the brightness at any other point from the observed brightness of the sky. The method consists essentially of excluding from the observed brightnesses local indicatrices of the diffusion and introducing another one which relates to the spot where it is desired to determine the brightness of the sky. For this purpose, it is necessary to measure at that point the brightness of the sky along the almucanter of the sun. A necessary condition thereby is that the transparency coefficients of the atmosphere be equal in both points. The theoretical brightness was also considered, taking into consideration the multiple scattering of light in the case of a spherical indicatrice of scattering, and a comparison is made of this brightness with the one observed at an angular distance of the sun of 57 to 60 degrees. For solving the integral equation of the theory of the diffusion of light, the approximate method of Kuznetsov was used, which proved sufficiently accurate. Diffusion indicatrices are given in the dissertation, which were obtained from observations of the brightness of the sky, calculated for the entire height of the atmosphere. It is shown that there is no well-defined relation between the coefficient of scattering for small scattering angles and the coefficient of transparency, or respectively the optical thickness of the atmosphere. Such a well-defined dependence does exist for diffusion angles approaching 60 degrees. Thus, the diffusion of light near V equals 60 degrees. It does not depend on the properties of the diffusion particles. It is shown that the diffusion of light in the Earth's atmosphere cannot be attributed to a medium particle with some definite effective radius. The effective radius of the diffusion particle changes with the diffusion angle. The dependence of the diffusion of light in the Earth's atmosphere on the wavelength for the visual part of the spectrum can be expressed by the relation U equals C lambda to the nth of the spectrum can be representing a generalization of the known Rayleigh formula, where n is greater than 0 and independent of the wavelength for all angular distances of the sun, provided the dust content of the atmosphere is not high. If that is not the case, this relation is disturbed and becomes somewhat complicated for small angular distances to the sun. the halo surrounding the sun. The number n is dependent on a wavelength, and in some parts of the spectrum may become negative. This explains the various color shadings of the halo surrounding the sun. A method is proposed of determining the indicatrix of the atmosphere, which is not affected by the influence of the multiple diffusion of light. This method permits obtaining the indicatrix solely from the observed data and consists in determining by two differing methods the optical thickness of the atmosphere. One method gives optical thickness on the basis of measurement of the direct solar radiation and is therefore not dependent on the multiple diffusion of light. In the other method, the optical thickness is determined by measuring the brightness of the sky and consequently is influenced by the multiple diffusion. The difference between these gives an increase in the optical thickness of the atmosphere, which depends on the multiple diffusion of light, i.e. of the diffusion in all directions of the light flux caused by diffusion of higher orders, relative to the incident light flux. The author gives the formula of the brightness of the sky, taking into consideration the multiple diffusion and also the light reflected from the underlying surface. The problem of stability of optical properties of the atmosphere was considered, and existing stability criteria were supplemented and improved by the author. It is shown too that the ratio of the brightness of the sky at any point of the almacanter of the sun to the illumination from the sun also gives a linear dependence on the atmosphere mass and consequently can serve as a criterion of stability of the optical properties of the atmosphere. Finally, methods are described of determination of coefficients of transparency of the atmosphere from the brightness of a clear sky, namely, a method based on the instant of maximum brightness of the halo surrounding the sun, a method based on the indicatrix of diffusion of light in the atmosphere, a method of determining the coefficient of transparency on the basis of empirical formulae. So, cutting to the chase there, as you saw, they actually mentioned that they prove that there is a firmament, that they're measuring the light of the firmament, and they know the distance to the firmament, and also that this is done assuming and knowing that the Earth is flat and non-rotating. There you have it, folks. There is a firmament. The Earth does not go on forever. It is not an unending plane. There is a solid firmament in the sky, as was told to us in Holy Scripture by the Most High, by God. So, thanks guys for listening. Don't forget to smash that like button and share and subscribe. I'll have lots more movies up soon. A lot of my movies that I've been posting have been being blocked, banned worldwide, etc. So we are doing what we can. I'm doing what I can to get my stuff posted and keep it up. Thank you for listening, guys. Have a great day.
You rev up your